Okay, so just a quick recap of what we did yesterday, which is an order of reaction. Order of reaction is the power that we use in the rate equation. Okay, so how do I change this? Hold on, yeah. I found. Okay, so how do we identify zero, first, and second order? Basically, for zero order, when you increase the concentration of your reactants, okay, what a particular reactant, if it has zero order, then increasing the concentration has no effect on the rate of reaction. Now, this is a bit odd because, as we know from our previous knowledge, that if you increase the concentration of a reactants, logically, the rate of your reaction will increase. Okay, the reaction gets faster, right? But this does not apply to reactants that are zero order. First order, this is the normal one. If you increase the concentration of a reactant, the rate of reaction increases by the same amount. Okay. Someone asked me in the last lesson, which is a good question. What happens if we, you can't hear me? Okay, hold on. Can everyone hear me? Okay. Okay, right. So it's just Nat. She couldn't hear me just now. Maybe it was her connection. All right. Thank you, Nat. Thanks, Shakirin. Okay, back to my slides. So for first order, if you increase the concentration of a reactant, the rate of reaction increases by the same amount, okay? So the question that one person raised after the lesson last time was that what happens if we decrease the concentration? Same thing, okay? If I decrease the concentration of a reactant by half, my rate of reaction will also decrease by the same amount, which is half, okay? So the effect is the same whether if you increase the concentration, the rate increases. If you decrease the concentration, the rate also decreases, okay? As for second order, the rate is proportional to the square of the concentration of A. So that means if I increase or if I double the concentration of my reactant, okay, the rate of reaction will go up by 4, right? You will see sometimes in textbooks or on the internet, they will use the term fold, okay, increase by 2-fold, and then increase by 4-fold, etc. This means increase by 2 times. It's the same thing. Fold and times is the same concept, okay? Right, next one. Okay, so this was an activity if we were to have this lesson physically, okay? Right, how do you identify orders of reaction? Okay, so this brings us to the next learning objective, which is to interpret experimental data in graphical form, okay? Right, so there are 3 ways to find the orders of reaction graphically. Okay, the first one is your rate concentration graph. You haven't seen a rate concentration graph yet. The second one is concentration time graph. This is something that you are familiar with. What happens to the concentration of reactants over time? So reactants will decrease over time. If we're looking at the concentration time graph of a products, it will increase, okay? The last one is half-lives, okay? So I'm not sure if some of you physics students have come across half-lives, but this is exactly the same concept of half-life as you would do in physics, okay? So half-lives can be determined from the concentration time graph. So please make sure that you do not get confused with graph number 1 and graph number 2, rate concentration graph and concentration time graph. It is important that you read the axis. Okay, Right, so this is an example of a rate on the y-axis and concentration on the x-axis. Okay, so what happens, basically we want to look at what happens to the rate, which is the y-axis, as you increase the concentration of your reactants. Now logically you would think, oh, increase reactants, the rate will also increases. But don't forget, there is this concept of zero, first, and second order. Okay, zero order, just now we said that increasing the concentration of your reactants will have no effect on your rate. Okay, so if you look at this, right, from 0 to 1 mole per dm cube, and then you look at the y-axis, it doesn't change. Okay, they stay constant, the rate stays constant. So that's how you identify zero order of reactant. Okay, in this case, the reactant that we use is still just a general reactant, reactant A. Okay, so the explanation for that, where is my, okay, right. So how do you read this graph, or how do you analyze it? Okay, so you just take 1 point first, right? I'm gonna start with 0.1 because that's the easiest. Okay, at 0.1 of concentration, my rate is 0.010. Okay, fine. Now what happens when I double the rate, double the concentration? So going from 0.1, that's 0.2, reading the rate, it is still the same, 0.001. So when I go from 0.1 to 0.2, that is an increase by 2, okay? Or we call it 2 folds, or we say double the concentration, okay? Doubling the concentration, no change in rate. Next, if I double again, going from 0.2 to 0.4, that's another 2-fold, again, times 2. But we look at the rate is still the same, okay? So that's significant of your zero order reactants. Now I can continue to do this up to 0.8, okay? So every time I go from 0.1 to 0.2, that's doubling the concentration. 0.2 to 0.4, again, increasing by 2 folds. 0.4 to 0.8 is again increasing by times 2. Sorry, excuse me. Right, so the reaction is zero order with respect to A. The concentration of A does not affect the rate of reaction. So in a rate concentration graph, you will see a horizontal straight line on that graph. Okay, whenever you see a horizontal straight line on a rate concentration graph, that is the identification for a zero order. Okay, I believe that you don't have this. You may copy that down on your notes. I'm going to unmute. Okay, are you guys copying this down?
Yes.
Okay, right.
Yes.
Let me know when you're done. I've unmuted all of you.
Okay.
So while you're copying down, I can have my breakfast. I actually have my bowl of cereal next to me. Have you had your breakfast?
No.
No.
Yes.
You can have breakfast after this. I mean, you're at home anyway. You can even eat while you're having classes. Are you not loving online class? I'm actually enjoying it because I can just wake up late and then I can have my breakfast while I'm having class. Are you okay, Nabil?
Yes.
Okay. Safina, how's the audio? How's my voice?
Yeah.
Is it clear?
Not clear.
Okay. As usual, I am recording this session. So, oh my God, I'm recording this session. I forgot about that. I talked about how I have my bowl of cereal next to me. Okay. Now, to continue, right? While I'm explaining, you can continue copying down if you are not done yet. Let me just clear this first. Okay. The graph on the right side is a graph of a first order. Okay. The rate concentration graph of reactant A that is first order. Okay. Just to make myself clear, if that one particular reactant is already zero order, it can only be zero order. Okay, so another reactant will be first order. They cannot change, like sometimes zero order, sometimes first order. So they will be fixed in the same reaction. Okay. Right, so let's see for this graph where we have the rate concentration graph of a first order. Okay, so ignore this dotted line that is already printed on your notes, right? But if we remember from our previous page that first order is when you increase the concentration, when you increase the concentration, the rate increases by the same amount, okay? So same thing, how do we know this is a first order? We just use an easy point first, 0.1. 0.1 is an easy point, okay? So if we read the rate at 0.1, it reads at about, I don't know, 0.006. I'm just gonna make that up, okay? Because I can't read it accurately because it's not a proper graph paper, okay? So at 0.1 concentration, the rate is 0.006. Now, I want to look at the effect when I double the concentration, okay? When I double 0.1, it becomes 0.2, okay? You may ask, why do I choose doubling? It's easier, okay? You can use triple, you can use quadruple, you can times it by 3, you can times it by 4. It does not matter, okay? But I like to just double it because it's easier. It's easier to work with times 2. So my concentration on the x-axis, I have increased it by 2-fold from 0.1 to 0.2. Now I'm going to look at the rate, okay? So I'm going to read the rate at 0.2. Hold on. Okay, so you can see now the rate was originally 0.06 and then now it becomes 0.012. Okay, so going from 0.006 to 0.012, that's also a multiple of 2 as we already know it. Okay, so that's times 2. So you can see the effect of increasing the concentration on the x-axis has the same effect on the y-axis. This is what we call linear, directly proportional. Okay, let's try another one. If I try to double 0.2 again to 0.4. Let's see. Okay, so that's my 0.4. As I said, just ignore the dotted dotted line that has nothing to do with my explanation now. Okay, so if I read the rate as I increase the concentration to 0.4 again, okay, if I read the rate, it would be around 0.024, okay? Before this, we were at 0.012. And then now it's 0.024. So that is a double as well, okay? If you see this, going from 0.2 to 0.4, that's an increase in 2 folds in concentration. But for my rate, which is on the y-axis, it also increases by 2. Okay, so that is how you identify a first order, a reactant that has a first order. Okay, the graph shows that the rate is proportional to the concentration of A. The rate constant K is the gradient of the graph. For a reactant that is first order, just remember that it is a straight line that passes through the origin. Okay, why? Because if you look at this, rate is equals to K times by A. I use a different color. Y is equals to M X plus C. Okay, so your y-axis is the rate, your x-axis is the concentration, so that makes your K as the gradient. C is y-intercept, which is 0. Okay, I hope that is clear. Any questions?
No.
Okay. Okay, let me just clear this. But I think you can see it, right? I am missing someone. Who am I missing? Kabit. Are you done copying?
Yes.
Okay. I'm gonna clear this. Next is the rate concentration graph of second order. Okay, so the rate concentration graph for second order is actually the one on the left. Okay, a curve that is increasing. This one. Okay, this is the graph of a second order. I'll talk about the graph on the right after this. Okay, now how do we identify the graph of a second order? Same thing, same procedure. You pick a point. Now at this, for this graph, if I cannot take 0.1 because I cannot read exactly what the number is. So 0.2 is also difficult to read. So I am going to take 0.4. Okay, so I just choose any number that is easy, any point that is easy. So if I read 0.4, the reading is again about 0.006. Okay, so I want to double my concentration. Now, doubling 0.4 will give me 0.8. Yeah. Okay. Why do I start at 0.4? No particular reason, because it's easier to read. You can start from 0.1, you can start from 0.2, 0.3 even, but I'm going to start at 0.4 because it's easier to read in this graph. So going from 0.4 to 0.8, that is increasing, that is increasing my concentration by twofold, okay, or doubling it like that. So I'm going to read the graph, what happens to my rate. At 0.4, my rate was 0.006. At 0.8, my rate is now 0.024. Okay, I'm just gonna make up that number. Now going from 0.006 to 0.024, how much increase is that? 4 times. Okay, so 0.006 times 4 is 0.024. Okay, so you can see that increase in concentration is by 2, but the increase of your rate is by 4. Or if you want to write it in like this, times by 2 square. Okay, this number 2 is the fault of your concentration. We increase the concentration by 2, but your rate will be the square of that increase. So times by 4. Okay, but if you are confused by that, then I will just omit it. Okay, so whilst it's easy to think that every curve that you see is of second order, you must not assume that a curve on the rate concentration graph is showing a second order, because it can be a third order, fourth order, and etc. But for your case, your syllabus only covers up to second order. So every time you see a curve, it is most likely to be a second order. Okay. But one thing you can say for sure is if you see a curve in a rate concentration graph, it cannot be zero order, it cannot be first order, because zero order will be a straight horizontal line. A first order will be an increasing line that passes through 0. Okay, to confirm if it is second order, okay, now if you plot a graph of rate against the concentration square, then you will get a straight line. Okay, why? Because if the reactant A is second order, this is how we write the expression of rate equation. Rate is equals to K times A to the power of 2. That 2 stands for second order. Okay, so if we plot the graph of rate against concentration of A square, I will get a straight line. For the same reason that this straight line comes from Y equals to mx plus c. Your y axis is the rate, okay, no problem with that. Now look at your x-axis. Your x-axis is now a squared, okay? That's why you see here, you plot the square of the concentration, then only you will get a straight line, okay? If you only plot concentration square A without squaring it, then you will see a curve, okay? So there is a difference. So you really have to look at the axis. If it's just A, it would be a curve. If it's a square, it would be a straight line, okay? Right. Now, don't worry about this, this second graph. The most important thing is the graph on the left. Please make sure you are aware of that, okay? So this is just to show all the zero, first and second order next to each other. You can see that they are very different. I will not go through it again. Okay, now this graph, you don't have it in your notes, which is fine. Okay, you don't need it. Let's see. Because it's exactly the same as the one above. Straight line is zero order, the red curve is a second order, and the blue increasing line is first order. Okay, so I'm just going to go through that quickly. Deducing the order, the next learning objective is deducing the order of a reaction from concentration time graph. Okay, so this is a different graph now, the second graph, and it will look different. Okay, this is how a concentration time graphs look like. Now, just to recap again, if we are to plot the concentration of reactants over time, okay, the concentration, you will start concentration at a certain amount, right? And over time, the concentration decreases, right? Sometimes it will go to zero, sometimes it will just flatten off depending on what happens at the end of the reaction. If all of your reactions is used up, then the graph will touch zero on the x-axis, okay? Now there are different, all three of them are decreasing, but they have slightly different shape, okay? For zero order, you will see a straight line showing a constant decline in concentration, okay? So you can see that decreasing the concentration over time, okay? We want to look at the rate. Now, rate of reaction, how do you find the rate of reaction from a concentration time graph? If I remind you that rate of reaction is equals to change in concentration over time. Can anyone answer me? How do I find the rate of reaction from a concentration time graph? Anyone?
Gradient.
Gradient, that's right. Thank you. Okay, so to find the rate of reaction, I can find the gradient. So look at zero order. The gradient at different concentration is the same. So that means even if I decrease the concentration, my rate will be the same. Okay, I take the gradient at this point. Hold on. Sorry. Okay, if I take the gradient at this point, or this point, or here, it is the same. The rate is the same. Actually, my concentration is decreasing, but my rate is the same. Okay, so this is the same idea. Decreasing concentration, rate stays the same, zero order. Okay. Now for first and second order, they will be curved. Okay. Now it's not easy to see because both of them are decreasing and both of them are also showing curves. But one thing that you can notice is the curve for second order decreases a bit deeper. Okay, or you can see if you one way, the best way to differentiate between first and second order is to calculate the rate. Okay, you have to find the gradient when the concentration goes down by half. Okay, what happens to the rate? And then as it goes down by half again, what happens to the rate? Same thing for second order. You take 1 point, calculate the rate, and then you bring it down by half, what happens to the rate? And then you bring it down by half again, what happens to the rate? And then you look at the relationship, okay? So I have this, right? This is how you find the rate of a reaction from a concentration time graph. You will draw the gradient, Okay, and then only you will read at this particular concentration, my gradient is this. At this particular concentration, my gradient is this. Okay, you cannot just read the x-axis. Okay, cannot say, right, if I take this concentration and then I read it here, the time is that, and then if I take it again, then the time is that. Right, remember, this is time. It doesn't tell us anything about the relationship between rate and concentration. You have to find the gradient. So in this case, you just have to memorize that zero order will be a straight line. Your first and second order will be a curve. Okay.
Miss,
Yes. Yep.
do we need to find for gradient for first and second order?
Yes. If you
That's
want
what you
to,
mean.
yeah. If you want to differentiate which one is first and second order, you have to find the gradient, because the gradient is the rate. You want to know the relationship between concentration and rate. Okay.
Do we need to find the grade? I mean the average.
Average? No, no, you don't find the average. Okay, there is another method that you can use for concentration time graph, which is the next one, right? Okay, so this is half-life. Now I only have 6 minutes left, so I'm just going to introduce what half-life is to you. I don't think we will have time to do calculation. Okay, so the next learning objectives is to explain and use the terms half-life of a reaction. So that's the first one that we're going to look at. Now, physicists, Fatin, have you guys done half-lives in physics?
Yes.
You have, okay, good. So the
Yes.
physicists will know this. Well, I'm guessing you're the only physics students in the class. Okay.
And criterion.
Sorry? Oh yeah, and Shakirian, yeah. Okay. So half-life can be determined or calculated from the concentration time graph. So you don't get confused, okay? What is the definition of half-life? Half-life, or sometimes written down as T half, okay? T here stands for the time. So half-life is the time taken for the concentration of a reactant to fall to half of its original value. That's what half-life is. Is that the same definition, Fatin?
Yes.
Okay, right. So remember, half-life is talking about the time, not the concentration. The concentration is just decreasing by half. But what we want to know is the time taken for the concentration to go down by half. Now, half-life can only be read off from concentration time graph. Why? Because by definition of half-life, the time taken, you read it from time, and concentration, you read it from concentration. So sometimes the definition is already a hint to you which graph to use. Okay? So that means you cannot find the half-life from a rate concentration graph. Okay, I know it is confusing at this point. Which one do I use? Which one do I find? I hope it will be more clear when we do questions or exercise later on. Okay, so this is your zero, first, and second order. How do we find half-life? Tomorrow, I'm going to teach you how to find half-life, but these are the features of your zero, first, and second order, okay? Basically, for your zero order, the half-lives will decreases. It gets smaller. For your first order, the half-life is constant. For your second order, the half-life is increasing. Okay, so again, it's something to memorize. You not only have to memorize the graph of a rate concentration graph for zero, first, and second order, you also have to memorize the graph of concentration time graph of a zero, first, and second order, and you have to memorize the half-life for zero, first, and second order. Okay? Right, so I'll talk about this. For a first order reaction, there is a formula that you can use. Why is there a formula for first order only? Because the half-life of first order is constant. So there is a formula that you can use to calculate it. For zero order and second order, the half-life is changing. Therefore, there is no formula that you can use. So I'll talk about this tomorrow. And tomorrow you will learn how to determine the half-lives from this graph. Okay, so that is the end of this session. I'm just going to